Hello everybody. In this lecture we will be going over 1986 IMO problem number 2. Here's a view of this problem. We're given a triangle A1, A2, A3. Let me go ahead and draw this triangle, I guess. A1, A2, A3, and then another point on the plane. So, well, I guess I'll pick this. I'll pick this point P sub 0, and then we implement the following succession of operations. So we will rotate P sub this point P0 around point A1 with a 120 degree angle. So this point, actually, let me pick another color, I guess. So let's do this. So this point here, that's the distance. Once we rotate it clockwise, no, so probably what? Over here, I guess. So that point becomes P1. And now we pick that point and rotate it around point A2. But the thing is, so this angle was 120 degrees. We will continue to rotate it again clockwise. So we'll go this direction, I guess. 120 degrees, so something like this, I would say, probably here. And this new point is P2 now, and this angle measurement is again 120 degrees. Finally, we rotate P2 around the point P3, again 120 degrees, so probably, I guess, somewhere here, but it will be way up there. Oops. So somewhere here is my point P3. Do you all agree? So this is 120 degrees. So, and we continue this process. Then from P3, again, we will rotate P3 around A1, and then around A2, A3, A1, A2, A3, in this succession of rotations. Actually, we will implement this operation quite a bit of times, actually 1986 times. But what's so surprising is after you do this operation 1986 times, you get back to your original point. How can that be? So the first observation I would like to make is the following. After we do those 3 rotations around A1, A2, A3 in a succession, right? We have 120 degree angles all the time on the same orientation, right? So we are constantly rotating our point around the reference point by 120 degree angles, right? So the claim is we make a full rotation of 360 degree angle after 3 of these rotations. So what I'm trying to say is that I claim the combination of these 3 rotations, namely we take our point P0 and we apply a rotation first to this point. This was a rotation around point A1. Let me just call it R sub 1. And then the outcome, which we know is P sub 1, this outcome is P sub 1. P sub 1 is rotated around point A2. And finally, from here we will get P sub 2, I guess. P sub 2 is rotated around point A sub 3, and we reach the point P sub 3. So what I will do is this composition, R1, R2, R3, let me just call it F. So F is equal to R3 composition R2 composition R1. This is in a sense function composition, right? So if you apply P0 to this, for example, what you will get will be P3, right? So that's but anyhow, okay, so let me erase this last part. F is this function here, and what my claim is, again going back to the question, my claim is that this is equal to a translation. So we have this vector V, this green vector. I claim that each time we repeat these successive rotations around point A1, A2, and A3, we'll get this this translation from from point P0 to P3, and then from P3 we will go to P6, so P6 will be somewhere here, sorry for messing up with the picture, and so on. So P9 will be up there, but then look at this given condition. So our triangle should be such that, or maybe our starting position, I don't know, so should be such that P 1986 is equal to P sub 0, right? And well, that gets me thinking, so how can that be? Because I'm expecting this after repeating this 1986 times, which is, if you divide 1986 I think by 3, that should give us, I think, what, 662. So we are applying function f repeatedly 662 times. I don't even know how to write it actually. F of P0, and you get again P0. How can that be? And we repeated this 662 times. Well, there's only one explanation. This translation vector is actually equal to 0 for this particular configuration of the triangle, because it looks like it's independent of the choice of P0, right? So what type of triangle will give us that nice feature, basically? Well, you might have a couple of good guesses. Obviously, one immediate guess most of us would do is, hey, it's probably the case that this triangle is an equilateral triangle, right? But we still need to prove it, and obviously that's the statement that needs to be proven, right? So good. So for that, what I will do is I will use some complex algebra, and hopefully that should do the trick. But first I need to create some more space for myself. Hopefully I won't mess up this thing too much. I begin with this all rotation tricks. Let me just remind you of a little bit of complex algebra. So consider you have a point, let's say here, z, a complex point. This is the real and imaginary axes, I guess, right? And I would like to rotate z. Well, I think this is redundant. I don't need that. Okay, so I would like to rotate z around, let's say, point W. That's W, and let's say for a given angle theta. When I rotate it by a certain angle, let's say angle theta around this point, so how does this happen, right? So z prime after rotation. Oops, that's not good. Sorry for that. Okay. Yeah. So how do I even think about this rotation, this theta? So the way it works is the following. So I will translate this vector here, obviously z minus omega, let's say somewhere here. So this is z minus omega. I will rotate it here by this angle. Rotating it by this angle here is basically multiplying it by CIS theta, right? So we know it. And then once I have the outcome, so z minus omega times CIS theta, all I do is I just translate, I just translate that point back to the original place, which is basically just adding back the omega. So and just to clarify, so this was omega, obviously, right? So all I do is I just add back the omega, so you will get a parallelogram there. So this guy is therefore equal to z minus, I guess, omega times CIS theta, plus we add back the omega. Okay, if this is clear, then we can go back to our question at hand. So when we rotate 120 degrees around point A sub 1, so let's call this rotation as R sub 1. So and obviously R sub 2, R sub 3 we can define in successive terms as well. So what we get is the following. So R sub, well, you can say for K equals 1, 2, and 3, at least for the first 3, R sub 1 is simply by the same logic, right? So R sub 1 of, well, actually, I can directly apply point r sub 1 of z. Let z represent the point p, right? So p0, or I should probably say. Okay, so r sub 1 of z will be equal to I guess z minus, so remember our reference point is point a1, so z sub minus a1, and then I will multiply it by CIS 120 degrees. No, it will be a negative, right, because it's clockwise. Remember this rotation was counterclockwise, so it will be CIS minus 120 degrees. Yes, that should work. So, and then we add back the a sub 1. Yeah, just to make our life easy, let's just call it something easier. Let's call it lambda. Okay, so in the second step, so I'll do the same thing for when I rotate it around point A2, which will be R2, and so on, right? So so if, for instance, I apply R2 to R sub 1 of Z, all I will need to do is, well, I have this huge point which I keep, right? So I still have Z minus a sub 1 times lambda, I guess, plus a1. Now I need to subtract a sub 2, my new reference point, multiply it by lambda, and then add a sub 2. And finally, we do it one more time for point A3. We rotate around point A3 counterclockwise 120 degrees. Yeah. So I have z minus a sub 1, lambda plus a sub 1 minus a sub 2, lambda plus a sub 2. Remember what to do, right? We add, we subtract a sub 3, close the parentheses, multiply by lambda, and then add back a sub 3. Whew! And that's our function f applied to the point z represented by applied to point p represented by the complex number z. Well, obviously a couple of remarks. I called CIS minus 120 as lambda, and as a result, so lambda is CIS minus 120, which is somewhere here, I guess, right? This is our lambda. If I multiply it, well, 3 times, meaning if I rotate it 3 times, I will hit here. Oops. That's lambda square. And finally, I will hit here lambda cube. So lambda cube is equal to 1. Okay, so if you guys are ready, let's do the algebra, I guess. So let's expand this monster here. So we have equal to, so when I expand with, well, obviously, I'll multiply this lambda across here. And then finally, I will expand this lambda across these terms. So it will be quite a few algebra. So I will have z minus a1 lambda cubed, right? So okay, sorry for that. Z minus a sub 1 lambda cubed. And then I will have, well, a1 minus a2, I guess lambda square, right? So plus a1 minus a2 lambda squared. Let's get rid of all these arrows, right? It's on my way, so get rid of it. Okay, what else? And then a2 minus a3 lambda plus a sub 2 minus a sub 3 lambda, and finally a sub 3, I should say, I guess, yes, plus a sub 3. Well, as I claimed earlier, so lambda cubed is 1, so this guy will come out as 1. So finally, this whole thing will be equal to z, and then this a sub 1, I will just move it to the end. So therefore, I will have this this expression, right? So what's going on, guys? Okay, good. So I have oops, come on, just help me here. A sub 1 minus a sub 2 lambda square plus a sub 2 minus a sub 3 lambda plus a sub 3, that last guy, and that guy here minus a sub 1. Look at that, huh? Let's just call this, what do you want me to call it? Let's call it W. And I claim W, this complex number, represents the early vector v that we talked about earlier, right? So this is our translation vector. Translation vector. It represents the translation vector v. So if you apply this 3 rotations, combination of 3 rotations, the function f, which is the composition R3, R2, R1, to our point p sub 0, you'll get your point p sub 0 and then this translation added. So it will be. However, we know that this translation vector is just 0, right? So we from the assumptions of the problem. So let me let me just write that down. So z sub 0, let's say for instance, representing our point p sub 0, is equal to z sub 1986, right? Which is simply equal to what? It's just simply equal to this f function composed 662 times, right, on our point z sub 0, and that's equal to z sub 0 plus 662 times our translation vector. And as I said earlier, this guy is equal to z sub 0, so therefore this guy is equal to 0, implying that omega, the translation vector itself, is 0 as claimed earlier. And yeah, so it's equal to 0. And let me go back to this original expression here, this omega expression. So now we know that 0, so omega is equal to 0, obviously. So 0 is equal to omega, which is equal to, look at this expression. In fact, I can apply this very nice and cute trick. I will be able to factorize this expression here, this whole expression. The way I will do it is I will factor out a lambda minus 1 here, and if you do the algebra carefully, so you should get the following thing, times lambda plus 1 plus a sub 2 minus a sub 3, and that's it. But look, so this whole thing is 0, suggesting either this first part is 0 or the second part is 0. Obviously, lambda minus 1 is not 0. Why? Because lambda itself is not 1. So this is definitely not 0, suggesting that the second guy has to be equal to 0. But then the second guy, making second guy equal to 0. Again, I just realize here that a1 minus a2, because our triangle has 3 separate points, they are not the same points, a1 minus a2 is not equal to 0, and similarly a2 minus a3 not equal to 0. So what we get is that so this whole thing will imply that, suggesting this thing being equal to 0 is what? Lambda plus 1 is equal to, so this whole thing being equal to 0, I can move this to the right hand side and divide both sides by a1 minus a2, so I'll get a3 minus a2 over a1 minus a2, and yeah. Now what is this left hand side? So going back to our unit circle here, lambda is here. Let me change my color, probably red color. If I add 1, I'm increasing the real part by 1. That's the point for lambda plus 1. And obviously, due to the nice symmetry here, this thing will be a 60-degree angle here. And this one is also 60 degrees, by the way. But therefore, lambda plus 1 is nothing but CIS minus 60 degrees, right? So do you all agree on this? So this is equal to CIS minus 60 degrees. But how about the right hand side? So therefore what it means is the numerator, you have a vector, I guess I should say. Oops, sorry for that. So we have this vector, point A3, consider this point A3 and A2. So A3 minus A2 is this complex number. and then a1 minus a2 is another complex number like this. Oops, so probably a little bit farther away, I guess, right? Yeah, so something like this. This is a1, so a1 minus a2 is this one, and we are told that a3 minus a2, so this is just the definition for a rotation, right? So it shows you the angle between these two complex numbers. So this complex number and this is minus 60 degrees. So it is minus 60 degrees. So we are told that a3 is simply the image of a1 under a rotation around point a2, right? So, but then this tells you that rotation will preserve the distance here and a 60-degree angle. So distance, 60-degree angle, and the same distance again. It shows you that a1, a2, a3, they form an equilateral triangle. And that proves the statement of the problem. Hope to see you guys in our next video.